Hello, my name is Güven Adal, and today I'm going to present my EE473 project, 3D Continuous Moving Table Scanner. This project focuses on implementing a moving table CT scanner and reconstructing images using projections from slices as accurate as possible. The datasets I used were lung and brain datasets for the simulation. MATLAB is used for implementation of the project. Datasets are loaded within sample data add-on in MATLAB. Dynamic processing algorithms are used for reconstruction of the images. As I stated before, the goal of the project was to implement a real-life case of moving table scan. During the table scan, the table is moving, so projections are taken from different angles for each slice. To reconstruct the slice, other angles should be gathered in order to use inverse radon transform. In this implementation, different angles are gathered within the durations of the scan, and with a dynamic programming algorithm, every scan is reconstructed with limited projections and limited angle scan interval for each slice. As for my methods, the radon transform, in order to see non-idealities, I have implemented a CT scanner in a way that it cannot scan in the interval from 0 to 180 for each slice. This was important because the rotation of the scanner was not always takes all the angles from 0 to 180. I have used 3D chest scan of lungs that is loaded with image processing toolbox in MATLAB with the low chest volume in the first line. It's a three-dimensional matrix which contains 318 slices that has 512 to 512 pixel images. I have selected the table length as 0.76 meters and table velocity as 1 centimeters per second. Slice length of the lungs is 0.0019 meters. Thus, scan duration for each slice is slice length divided by table velocity. Uh, Number of projections CT scanner can gather for a second is taken as 200, which can change from the scanner to scanner. Number of angles that is gathered from each slice is scan duration multiplied with number of projections per second. Slow CT scanners has a rate of 15 RPM, which is equal to 0.25 RPS, which is equal to 90 degree per second. Each slice is scanned and taken projections with the interval of the starting degree, which is the rotation of the scanner in the beginning of the scanning of a new slice, and the end degree, which is the scanning degree plus the degree change for each slice. Starting degree rotation of scanner when new slice scanning begins, and end degree starting degree plus rotation degree per second multiplied with scan duration. Table is formed with number of columns equal to the number of projections multiplied with the slice number. Row size equal to the radon transform of the result row size. With a certain period, each column corresponds to the same degree in the modulus of 360, taken from a different image. This period is equals to 360 divided by degree per second multiplied with scan duration plus scan duration multiplied with scanner projection rate. This is used for creating a reconstruction table. The reconstruction table is three-dimensional table which every image is radon transform is stored. Selection of the projections of different angles to form the radon transform is done here. Algorithm forms clusters from the columns of dynamic processing table and checks how many projections are taken to form one full rotation. Then algorithm looks at the closest column corresponds to the projection degree, which it needs to form a radon transform of the corresponding image for each column between the interval of two full cycles. Closest column corresponds to the required degree is taken to the closest projection, which hasn't been obtained from that slice because the rotation doesn't fully cover all of the angles as I have stated before. So I choose the closest slices degree, column degree for reconstructing that slice. As for my results, we can see now 3D volume of the chest volume dataset, which no reconstruction has done. This is the dataset of chest volume. Now I have printed and plotted different random slices from the dataset. As I have stated before, there are 318, and we can see slice 100, slice 150, slice 200, and slice 250. Reconstructed radon transforms for these slices can be seen. And now we can see the algorithm I have developed. It reconstructed all the four different random slices. This is for in the image. As you can see there in image 2 and image 4, the reconstruction was really accurate, and this can be better understood by seeing the next slide. In here we can see the reconstruction of slice 200 without the method I have developed, with 95 projections between 0 and 45 projection interval. I'm showing this because the projections that is taken in this image for slice 200 also 95 projections between 0 and 45. If the reconstruction table is not used and only projections taken from this interval with this many projections, resulting reconstruction is not accurate at all and doesn't mean anything. But with the similar slices projections method, the reconstruction is way more accurate, as we can see from here and here, and this is a non-accurate version without the method. Now this is the 3D reconstructed volume of the lung dataset. I have done the same thing for a brain MRI dataset because I wanted to show both CT and MRI. This is the original slices, and these are the reconstructed slices. And again, I am showing the slice 5 without my method, with the same number of projections that I have used with my method. As we can see, reconstruction with my method was way more successful, and this is unrecognizable. And this is the 3D reconstruction of the brain MRI dataset. As I have stated before, in ideal MRI scan or a CT scan, enough number of projections are taken from a slice 0 to 100-degree interval, and in real life CT MRI scan, there is a continuous movement during the scan. Thus, not enough projections are taken from each slice. Possible problems are for my implementations are projection interval for all slices might be so small, not all degrees can be covered during the scanning. Also, with wrong adjustments, projection interval might be large, yet number of projections might not be sufficient enough to reconstruct. As for the demo of my code, I'm running it now. It takes approximately 1 minute for each dataset. When the results are, the code is run and the results are shown, I'm gonna show. Code has finished running, so I can show you my demo results. Here we can see the 3D volume of the lung CT dataset. Here we can see the 4 random slices that is shown from the CT lung dataset. These are the reconstructed lung CT slices. Here is the reconstructions made with same number of projections, but without the method. As we can see, it is not that accurate. And here is the reconstructed lung CT dataset that is created from the reconstruction of all the images. For brain MRI, these are the 4 random slices from the original dataset. These are the reconstructed brain slices as discussed in the presentation. We can see here the slice 5, but without the usage of the method, with the same number of projections and the same interval of projection. As we can see, it is not accurate. This is the 3D volume of the original brain MRI dataset. And this is the reconstructed 3D volume of the brain MRI dataset. Thank you for watching.